Okay, so in my previous lecture I was talking about the expansion of crossbars using crossbar, basically building up a larger switches using multiple of them in multi-stage interconnection configuration. We figured out that 2 stages cannot give me strictly non-blocking property, but 3 stages probably can, and I will show yes they can, and this requires much less cross point complexity compared to using a single crossbar of the same size. Okay, we will actually show that. But before we do that, we would like to actually look into how we will estimate the blocking probability of a system. And then of course there are two kind of blocking estimations, blocking probability estimations, that we need to also learn to differentiate, and we need to also learn how these two are actually related to each other. So I will start with a very simple crossbar, which is m by n. So remember, I am not taking my inputs are not same as the outputs. Okay. So I am actually having m lines which are coming in, and there are n lines which are going out, and these are like the telephone communication which is happening. The calls will come and calls will be then connected to some outgoing line. So if a call comes on this line, this will be connected and call is through. Okay. So the rate at which the calls will come here will be defined using a Poisson statistics. That actually means a point event on a time horizon. I will take time difference, time duration of t, how many events are going to happen. So if I actually assume the calls do arrive and they are instantaneously completed and instantaneously removed. So event happens and that is it. Normally whenever a phone call will come, it will be held up for certain time, so line will get occupied, new call cannot come. But if that is not happening, at what rate the call will be coming when call is not going on. So that we will define using a Poisson statistics, which is a commonly used model. So we define something called lambda, which is the number of calls per unit time. We call it a call arrival rate, okay, or arrival rate. This also is being used, this technique is also used for packet switching systems also. So in time t, lambda into t calls will be arriving on an average. Okay. So the probability, if this is a Poisson statistics, the probability that n calls will be coming will be arriving in time t will be given by, now remember, when the call is arriving, it is being instantaneously served and line is made free so that new calls can come in, because if you occupy the line, new call cannot come in actually, then I cannot make this estimate. So lambda t raised power n e raised power minus lambda t divided by n factorial. So this will be the distribution. Okay. So if you look for the probability of no call being arriving here, probability of one call, probability of two calls arriving in time t, and so on, the total sum of these are all mutually exclusive events. So when one call is arriving within time period t, two calls will not be arriving. When two is arriving, one will not be happening. So these are all mutually exclusive events. When I sum up all the probabilities, they should be equal to 1, which actually implies that summation of lambda t raised power n e raised power minus lambda t by n factorial, they should be equal to 1, which is obvious because so n goes from 0 to infinity, and this is nothing but a series expansion for exponential. So this will be written as e raised power plus lambda t, which turn out to be equal to 1. So this is a probability distribution, and we call it Poisson distribution actually. Okay. So that is what is happening. When the line, when actually in real life when a call will come, people will start talking. So there will be some time after which call will get cleared. Okay. So I define that the call duration is exponentially distributed, that is my assumption. Is exponentially distributed, and the mean value, mean duration, okay, for every call is 1 over mu. Okay. This also comes, actually can be derived from Poisson statistics. So, before I move further, I need to clarify this. So, I had defined lambda t raised power n e raised power minus lambda t by n factorial, that is a arrival statistics. But if I want to measure between two consecutive arrivals, what is the time duration? Let me find out the statistics for this time. Okay. So, I want to figure out a PDF, but for finding out a PDF is probability density function. You can always take probability distribution function and do the derivative of this. And if the variable is t, it has to be divided by t, derivative has to be with respect to t. So, I think this is very similar, that your x is less than x, that gives you the your PDF probability distribution function. You take the density, you will define something like probability density function. So, the variable x is going to be in range x plus x to x plus dx. Within this range, the probability that x will be lying within this is always given by px x dx. Okay. That is what the density actually means. And when it is a probability distribution function, this defines probability that x will be having a value smaller than this capital X, that is a PDF. Okay. And this is incremental technically, that is why you have to take derivative of this to get this. Okay. When I can use this same mechanism to estimate the exponential distribution for the time. So, Poisson distribution is related to exponential distribution. In that sense, the time between two consecutive arrivals actually is exponentially distributed. So, this can be estimated by, if the time is t, t is less than some capital T, the inter-arrival time is smaller than this will happen. This probability is nothing but that probability that you have more than one or more arrivals in time t. Okay. And of course, this actually means 1 minus there is no arrival in time t. Okay. So, this I can use this same expression Poisson thing, 1 minus no arrival when n is 0, this will be e raised power minus lambda t, and this is nothing but a distribution function, see here. So, I need to just take the derivative to get the density. Density is the probability that the value of x is going to lie between x to n x plus dx divided by this differential. So, this is the probability, and so this pxx will be given giving you the density function. So, let us take the derivative of this. This will give me now remember this, the random variable here is capital T. So, this is time. So, I can actually replace it by small t also, and if I take this, if this is a PDF, the area under this should be equal to 1, which is actually true if I take lambda e raised power minus lambda t dt. Now, this t cannot be negative, this can only be positive. So, it can take value from 0 to infinity, this will be equal to 1. So, this actually can be proven. Now, this time exponential, this is the exponential distribution. So, I can represent that how many calls will be served or how many calls will be finished essentially is the service rate. The mu number of calls will be serviced per unit time by the line, that essentially service rate will be decided by the call duration, average call duration. So, that is also essentially being assumed to be exponentially distributed. Okay. So, with this actually now I can analyze this switch and try to estimate what is the blocking probability. Now, before that, when the blocking is going to happen, if my number of outgoing links n is greater than m, will there be a blocking? Whenever a call will arrive, call can always be connected to an outgoing link because it is available, and when you are talking anyway, the call cannot come at your line, only on the free lines the call can come, but you will always find an outgoing link, so there is no blocking here. So, blocking will only always happen if n is going to be less than m. So, when n is greater than or equal to m, then blocking will not happen, blocking will happen only in this case. So, what is the blocking probability? So, I have to find out that's all, what is the probability that all the lines here are going to be occupied, we need to estimate that. How to do this? So, we can actually use here Markov chains, the concept of that. So, the idea is that I will identify the state of this switch. If only one line is busy, switch is in one particular state, this line can be anybody, it does not matter. So far one line is busy, switch is in state 1, when no line is occupied, switch is in state 0, and so on. I can actually then be in switch, can be in state n, when it is in state n, m is larger than n, so there are some free lines, call can still come in, but they cannot go through. So, switch is in blocked state. So, probability that this switch is in state n will give you the probability of the switch being in blocked state. Okay. This estimate or this number will be actually useful to us at some later point of time, when we will actually start doing estimation for a 3-stage interconnection. So, when your switch, so what I will do is I will represent these small round circles will represent states. So, I can actually be in state 0, I can be in state 1, I can be in state 2 and so on, I can be in some state I and I can be in some state n. In fact, truly speaking, if this one line is occupied, all other are free, this one particular state, next line is occupied, all others are free, is another state, but they are equivalent states, because there is only one outgoing line which is occupied. So, I am actually not, I actually have reduced my state space by merging all the equivalent states. So, there are only n non-equivalent states which are possible in this system. So, when you are in state 0, there is no call. I need to find out at what rate I will be transiting to state 1. So, with lambda number of calls per unit time the calls are arriving, what is the probability that a call will arrive in any one of these lines? So, if there is only one line which I will consider, probability that one call will be coming in some time, elemental time delta t, I am going to take it is very small time, and as we will solve, we will figure out this delta t is immaterial, because it cancels out when we will try to estimate the state probabilities. So, I can use the Poisson statistics. So, this will give me lambda into delta t raised to power 1. In fact, I can estimate the probability for 2 call arrivals also in time delta t, but delta t I will take so small that probability of having 2 calls will be still smaller actually. So, and then of course, I will have 1 factorial, and in limit when this delta t goes to 0, this will turn out to be nothing but lambda into delta t. So, that is the probability, or that is a instantaneous probability in small time delta t that one call will be arriving on one line. There are m such lines. So, the probability that one call will arrive will be given by m into lambda delta t, that is the rate at which the calls will be arriving. So that is the transition rate for going from state 0 to state 1. Okay. Now when you are in state 1, there is only one call which is going through. Remember, it is like I told you that exponential distribution and Poisson distribution are related to each other. So it is like there was only one call and this call is going to be serviced, and there is only one server and the service rate is mu. So in time delta t, mu into delta t e raised to power n e raised to power minus mu delta t by those many calls will be served. So probability that n calls will be served is mu delta t raised to power n e raised to power minus mu delta t by n factorial. Since there is only one server, only one call can be served. So in time delta t, when delta t goes to 0, n service to be given. So when I am looking for n is equal to 1, this becomes mu into delta t, that is the service rate. If the two lines which are occupied in time delta t, it will be 2 mu delta t, that will be the service rate. So I can actually come from 1 back using mu into delta t. When you are in state 1, one line is occupied from this side. The free incoming lines are m minus 1. So the rate at which the calls can arrive is m minus 1 into lambda delta t, and where you are in state 2, there are two calls which are there. Within small time delta t, the probability or chances, this basically is the probability, transition probability, okay, in a small time delta t. Remember, it is a probability expression which have been approximated as lambda delta t. This is a probability expression. So chances are that it will be 2 into mu into delta t. Now important thing is that if I want to, if this is a system which is in a steady state condition, so the probability of being in certain state will not change, it will remain, it is a constant actually. And something can always remain constant. If I take any closed surface in this is known as Markov chain. This is called Markov chain, and this is being used extensively for in queuing theory for analyzing the queue's performance. So this is also technically a queue. So if I take any closed surface like this, so the rate at which you are going to move out of this surface and rate at which you are coming into the surface has to be equal if the switch is in a steady state, which implies that probability that you are going to be in state 0 is P0, and that is a probability of transitioning going from 0 to 1. So that should be the transition rate now, should be this, and this should become P1 mu delta t. Now interestingly, this delta t gets cancelled because it is common on both sides. You actually make any closed surface here and build up a balance equation. This is known as balance equation. So the rate at which you will go out of the surface and rate at which you will come into the surface has to be equal, okay, because this system is in a steady state. Under that condition, delta t will always cancel out, okay. So ultimately we normally when we build Markov chains, we do not write this delta t because of this condition. When I put delta t, it is a probability of the transition taking place, but when I am not putting delta t, this value can actually be more than 1. Remember, probability cannot take a value more than 1, that is why delta t was multiplied. Ideally it should be probability, is a transition probability going from one state to another state, what is the chance it will happen. So that is what we do in finite state machines, okay. So delta t now actually can be removed. So ultimately how this whole chain will look like. So chain will now look like, it will go from here m minus 2 lambda 3 mu So, I have written these are basically now become transition rates, not the transition probabilities actually. Okay. So, the probabilities are proportional to this. So, proportionality constant delta t is being removed out. So, balance equations it does not matter actually. So, now I can actually use a balance equation to solve it. My idea is that I want to figure out what is the probability of being in state I. I want to estimate that. Okay. So, once I know the probability of being in state I can find out the probability of being in state n, which is the blocking probability of this system. So, let us write down the balance equation. I can write down in many ways. Okay. So, one of the possible ways is this. So, I can actually take a closed surface around every state and then write down the balance equation. So, balance equation around 0 will be P0, the outgoing rate is m lambda, this should be equal to incoming rate which is P1 mu. Okay. So, which gives me P1 as I can solve it m lambda by mu P0. I can look at the second surface and write down my equation. This will turn out to be P0 m lambda, that is the incoming rate. One incoming rate is from this side 2 mu P2. The outgoing rate is mu P1 plus P1 m minus 1 lambda. Okay. So, I just need to have a relation between P2 and P0, that is what I want. I want to represent all state probabilities in terms of P0. Okay. Once I have that, I can use some fundamental axiom of probability to figure out what is P0, and henceforth I can actually estimate all state probabilities. So, I need to put out P1. So, let me put the value of P1 there so that I can get P2. So, this P0 also I need to move on that side. So, this will turn out to be m lambda P0 this term comes on this side, it will become P0 m lambda. So, this cancels with this and this mu will become mu square, this will be 2. So, ultimately you will have alternatively I could actually have taken a surface like this. So, incoming rate has to be equal to outgoing rate and you would have got this equation directly. Okay. So, this would have become a relation between P2 and P1, and P1 I could have replaced from the previous one to get this particular equation. So, doing it this way for this surface, when I am taking enclosing this P1 m minus 1 lambda should be equal to P2 2 mu. So, which becomes P2 is equal to m minus 1 by 2 lambda by mu P1, which is I can actually keep on doing it. So, ultimately I can find out what is the probability of being in state I. So, this will be probability of being in state I will be given by m minus 1 m minus I plus 1, okay. Remember there in the brackets, okay, and of course I into I minus 1 into 1, and here it will be lambda by mu raised power I p 0. Now what is this expression? I think right. So, this particular expression is nothing but a combinatorial, it is MCI, m factorial, m minus I factorial and I factorial. The lower part is I factorial and this part is what gives you the numerator here. So, I can write Pi as m combinatorial I lambda by mu raised power I into P 0. So, for every state the probability now can be represented in terms of P 0. So, now let us solve for what the P 0 will look like. So, to find out P 0, remember all the states, switch always has to be in one of the states. So, sum of all state probabilities has to be equal to 1. So, technically sum of all mutually exclusive events, all possible of them, and the probability of those events being happening, when you sum up all the things together, that should be equal to 1. That is a fundamental axiom of probability. So, we will use that. So, P 0 plus P 1 plus P 2 and so on plus P I and P n should be equal to 1. So, which I can write now P 0 as 1 plus m C 1 lambda by mu raised power 1 this should be equal to 1, which gives me nothing but P 0 is, this is not a closed form solution. If n would have been equal to m, then I could have got a closed form solution. Here I cannot, okay. So, P 0 into summation of I going from 0 to n m C n lambda by mu raised power I is equal to 1. So, P 0 is 1 divided by summation of I is equal to 0 to n okay. So, you can now find out what is going to be probability of being in state I, MCI in fact I should write a different index here. So, I can put J. Because I have used I here. So, I have to use this. So, this is the probability. Now, what is the probability of being in blocked state? So, what is the blocked state? When the switch is in state n, and when I do that, probability of switch being in blocked state, we call it also as a PB, okay. Probability of being in blocked state, that is the way I will be representing this. So, this will be MCN lambda by mu raised power n, summation I goes from 0 to n, but that is a blocking probability for a m by n composite switch. We call it m by n composite switch. And this also is known as Yang set distribution.